Okay, so you all should be seeing my presentation now. Again, thank you very much, Rachel, for the introduction. To everyone who here can watch, good morning, good evening, and thank you very much for coming. As Rachel had mentioned, I'm from the University of Central Florida. I recently graduated with my PhD, and I'm currently postdocing here. I'm very excited. My focus was in rotating detonation engines, which you'll probably get to understand a bit more as I get into my presentation. So for my presentation today, I have the effects of fuel partial premixing on rotating detonation waves. I'd like to thank some of my co-authors here, Dr. Taha Razag, who is also postdocing at UCF now. And at the time of this research, my research advisor, Dr. Kareem Ahmed. We're at the Propulsion Energy Research Laboratory over in University of Central Florida, Florida, United States. I'd also like to thank some of the other agencies that we've worked with, Department of Energy, Air Force Office of Scientific Research, and the National Energy Technology Laboratory. So I'd like to first start off, I know with a lot of the presentations that have gone in the past, a lot of the focus has been on the research, and that's very much coming from the Young Researchers Forum here. One of the things, though, that I would like to mention, and this kind of goes hand in hand specifically with the rotating detonation engine, is technology readiness level. This is something that NASA, which is the Space Administration in the United States, had coined, and some of the other agencies in the United States have also grabbed onto this metric. But it's essentially a measurement system used to assess maturity level of a particular technology. It's a rating system from 1 to 9, where TRL level of number 1 is a paper concept, so it's very much just an idea or breakthrough. And eventually it works its way through the levels until TRL 9, which is a fieldable concept. So this is something that can be used in conventional technology. This is something that can be used by civilians, by governments, and so on and so forth. One of the things I'd like to really key here is that the RDE is foremost a technology, and kind of secondary, it's a research bed. A lot of fundamental detonation work is very difficult to do on a rotating detonation engine, and thus a lot of its use is primarily for direct applications for propulsion or power generation applications. So right now, the RDE, a rotating detonation engine, is actually sitting somewhere between a TRL3 and TRL5, depending on who you talk to. And that corresponds to system and prototype validation. So we don't see quite yet rotating detonation engines in our airplanes or in our power generation gas turbines, but we are seeing system and prototype level tests, again, at universities, as well as also research laboratories and some small businesses. So a lot of work over the past 7 years has pushed us to this point. And it's expected that within the next 10 years, we should be able to hit TRL 9 of fieldable concepts. And again, the reason why I bring this up is mainly to put into perspective just kind of the work that we do here as young researchers. But typically, technology starts as a breakthrough, as a eureka moment. It enters into this kind of research feedback loop where eventually we initially start off with fundamentals to try and understand what actually happened and how we achieved that breakthrough. That feeds into application, where we then put this into experiment. We put this into numerical simulations, and we actually test this rigorously to understand what are the bounds. And based on the information there, we feed back into fundamentals, and we continue going through this loop where we inform fundamentals with the applications and so on and so forth until eventually we hit a high technology readiness level, and this gets pushed out as a technology. And I just wanted to cover that a little bit because I know a lot of the juicy bits that I'll be getting into in terms of the research. I just wanted to cover some of the non-research aspects first. So this might seem a little bit, redundant to given a lot of the really great presentations that we've currently had this semester already. But I want to start off a little bit on combustion. So performance and limitations of propulsion and power generation is influenced by the operation of the combustion system. Engine technologies operate on the principle of performing work, and this is actually kind of what I use to teach some of my students in my propulsions class, where your work can manifest itself through energy via 2 channels, pressure and temperature. So every type of engine or power generation system you have is all on the basis of increasing your pressure and increasing your temperature, either to have thrust or useful energy. So conventional combustion, one that we're probably most familiar with is your constant pressure, your Brayton cycle. where when you burn your fuel and your air, or you burn your reactants, you get a temperature rise from your combustion mechanism, but that is kept at a constant pressure, or sometimes with non-idealities, you actually have a bit of a pressure decrease. However, though, in the term of constant volume, that is another mode of combustion that falls under the Humphrey and Fickett-Jacobs cycles. Very much like it shows here, during your combustion, during your burning process, you are kept a constant volume, whether it's confined by a physical geometry or whether it's confined by high pressure waves through acoustics or potentially detonations. But essentially, during the combustion process, not only do you have a rise in pressure, you also have a rise, not only a rise in temperature, you also can have a rise in pressure. Because of that, if you look at this figure here in the middle, that extra triangle that we have here on the top, which is your burning phase, that is your extra energy and thus work that you can provide to your system. That improves your thermal efficiency and can mean all kinds of things like cost savings and performance enhancements. So your constant volume combustion, which is also oftentimes coined as pressure gain combustion, just to highlight the addition of what constant volume combustion can provide, can manifest itself under two types of combustion modes. One of them being deflagration, where your burning is subsonic velocities, versus detonation mode, where your burning is coupled with a shock wave at supersonic velocities. So a little bit more on pressure gain combustion. These combustion modes, as they fit into constant volume and constant pressure combustion. So I just want to talk about a few of the technologies that have been worked on thus far. So if we think about deflagration, constant pressure combustion, this is what we have today in a lot of our conventional engines. We have our internal, external combustion cycles, auto, diesel, dual cycles under deflagration combustion. However, though, we also under deflagration, so subsonic burning, we have the wave rotor and pulse resonator combustors, which I have some pictures here on the bottom of the slide. With the resonance pulse combustor, as I mentioned before, you can get constant volume combustion and a pressure gain by essentially containing your burning process within some type of confined volume or by acoustic pressure waves, which is exactly how the resonant pulse combustor works. Similarly, with a wave rotor, you actually have a geometric boundary where you fill channels in a rotor, you combust while they're closed, so you can realize some kind of pressure gain. However, though, also moving into the other mode of combustion, detonation mode combustion, we have a lot of different engine configurations there and combustor configurations. The pulse detonation combustor, rotating detonation combustor, as well as the standing and oblique detonation combustors, which for some of those, I have the pulse detonation combustor on the top, a picture of that on the top right, and the rotating detonation one on the bottom right, which is the topic for today's research. So going more into that, just again, a lot of you have probably heard about rotating detonation engines, but just to highlight a bit of its operation again, for those of you who are not familiar, I'm pointing to this picture in the top left. Essentially, it is an inner body and an outer body that confine a cylindrical, we call it annulus, combustion chamber, where on one end, we inject our reactants, our fuel and our air, or fuel and our oxidizer. We then induce a detonation wave through some kind of initiation process, which will feed on those highly turbulent, highly mixed propellants or reactants as they're entering the chamber, such that your detonation wave can continually propagate along nearby those reactants and have your hot, high pressure and high temperature exhaust gases feeding out the other end. So some things I'd like to highlight. It's considered to have relatively simple operation. Now, I don't mean that so much in terms of the physics and understanding, but in terms of the fact that it's very basic geometry and it's very compatible to a lot of our systems today. It would be, I wouldn't say relatively simple, but it could be straightforward for integrating rotating detonation engines and replacing them as our current combustors that we have today. Second thing I'd like to highlight on it is that we consider it quasi-steady and continuous, given the fact that the rotating detonation waves can continue to propagate as long as it's being supplied sufficiently well mixed and sufficient reactants. I mentioned quasi-steady because in the end, you still have a detonation wave rotating about in a circle where you have high frequency pressure fluctuations, which, for example, integration upstream of a gas turbine, it's very difficult to be able to model and understand what the exit flow is going to be like. That is something, though, that's been studied quite a bit in how we can take the exhaust of the RDE and uniform it both spatially and temporally. And that also kind of fits into my third topic, is that it's still largely underdeveloped. As I'd mentioned at the very beginning of the presentation, there's a lot that we don't know about RDEs, but there's a lot that we can get if we can utilize this technology. So one of the things I just wanted to cover, and especially because we have such a diverse audience, which is wonderful, there's a lot of different names that this technology kind of falls under. So I have a little table here on the right, which shows kind of some of the different combustor and engine nomenclature that is used for the RDEs that I've seen across literature internationally. But a few things I do want to cover is that there are a few specific variations of the RDE that are getting more and more common. The cylindrical RDE, which there's a picture on the bottom left, where you essentially remove the inner body and you inject from the outer body, or you inject radially. There's a lot of work that's been done on this in Japan. And then also the disc RDE, which is that picture in the bottom middle, where essentially you take your annulus and you flatten it down into a disc shape where you're injecting radially, and oftentimes you can integrate this directly with a nozzle for a lot smaller and shorter form factor. So more on the introduction of the RDE, this kind of goes without standing. There's probably been a lot of backgrounds that have covered this, but there's a lot of groundwork that has gone into even just developing the RDE as a technology. So in the late 1800s, with a lot of fundamental detonation work, as well as also as that continued, we pretty much had to build on 100 to 150 years worth of detonation research, hypersonics research, in order to be able to get to the point where around 1958 and 1960, where Wojtkowski of the Laurentiev Institute of Hydrodynamics at the time had been seeing in rocket engine development combustion instabilities, high pressure combustion instabilities that were originally taken as acoustic modes. They were very destructive because of their high pressure and high temperature, and they would actually blow up rocket engines. But they thought, what if these can be tamed? What if these can be utilized for engines? So thus was the development of the rotating detonation engine. Similarly, here in America, we also had a group based on our own rocket engine development that it kind of came across the same features, and thus kind of came across the same conclusion. What if we can take this and we can turn this into something more than just a bad thing that happens to our rocket engines? So I have here some pictures of just some of the great phenomenal work that has been done just here, and this again is just kind of the tip of the iceberg. And if you'd like to learn more about that, I have some references for those figures. But really, this has been an international effort in terms of looking at RDEs. It seems like every day I can go on to Google Scholar, or I can go on to ResearchGate and find a new research laboratory or a new university that's working with rotating detonation engines. So it's very promising. Here, I just highlighted some of the major countries that have worked with the rotating detonation engines. But even then, this is probably inaccurate as of a few months ago when I'd originally made this figure. But just to show, there's been a lot of work with integration, and especially between research laboratories and universities. There's been a big push for both integration in terms of propulsion, as well as also integration in terms of power generation. So going on into the background of the specific experiment that we ran here at the University of Central Florida, we had developed a 6-inch or just over 15 centimeter diameter rotating detonation engine design. It was based on a very similar architecture that was developed by the Air Force Research Laboratory here in the United States. It was a configuration that they had actually publicized and distributed to kind of have a common ground that people could look at the design, they could build it, and they could test it. And thus we had some kind of common test bed that universities and research labs could work with. So it was based on that design. I have a picture here on the bottom left of that RDE. It operates nominally with hydrogen and air as its reactants, hydrogen for its fuel, air for its oxidizer. When I say that it's reliable and well-tested detonability, as I'd mentioned, this was a very common architecture. This was something that had been distributed to quite a lot of universities and researchers. So there's a lot of data out there in the community in terms of its operability limits, as well as also just all kinds of investigations with hardware very similar to this architecture. And by reliable, I mean that the injectors themselves were designed such that you had a pretty wide operability regime in terms of when you get detonations and when you get either other types of deflagration modes or unstable detonation modes. Specifically, our architecture was made of an aluminum body with steel injectors, stainless steel injectors, and we initiate with a shell and spiral pre-detonator. A bit more on the body geometry here I have on the bottom of the slide, but also in the middle, just showcasing the inner body, the outer body. But what I primarily want to talk about is the injection scheme. So in the middle, you can tell it's centrally fed our air, and then we have axial discrete fuel injectors. And on the far right image, I kind of show a bit of the flow path and how we have mixing here. So it shows the discrete fuel injectors, which are denoted by the red arrows. The green arrows is such that our air or oxidizer is injected by a radial slot, such that you pretty much have a constant domain in a sense of air, where then we have our discretized 0.89 millimeter diameter micronozzle injectors. And because of that, we actually originally thought, based on this type of injection scheme, that we might have regions of high of fuel richness versus regions of fuel leanness, and that's just because of the injection scheme. But then that kind of feeds into a bit of the motivations of what we wanted to look at with this architecture, is that at least simulation-wise in the community, what we found is that detonation propagation in mixtures with concentration gradients typically propagate slower than in homogeneous mixtures. And this might be something that we kind of, take for granted, the idea that detonations like to propagate in well-mixed environments. So obviously it should mean that a detonation does not like to propagate through an environment that is highly stratified, where you have a lot of fuel rich and a lot of fuel lean zones, and these could be big zones. But it's found numerically that that is very much the case. We are proving what seems to be pretty trivial, and that the detonations don't favor that. And if anything, they actually propagate at slower velocities. So I have a figure here on the left, as well as also in the middle. There was another study in which it was found that within your rich fuel stratified zones, your triple points would extinguish. It would extinguish in the regions of air where you're very fuel lean, and then reform again when you have the introduction of fuel in your fuel rich zones. And the triple points are critical in terms of hotspot generation for your detonation cells, which have kind of been seen as an indicator of stability of your detonation propagating in general. So it's been seen numerically that stratification is not good for detonation propagation, or at least for stable detonation propagation. But one of the things that we thought of is, can we confirm if this detonation velocity deficit or change or distribution can be seen experimentally? Because a lot of what we've seen has been numeric. Is there any actual, reason for that we can see experimentally? So that's, I get back in, that was the motivation for the test that I'll be showing here today. A bit more on some of our operation. So how we operated this RDE is that we had a main fuel line that was regulated, actuated, and controlled, that we'd feed our hydrogen in through into our rotating detonation engine. We also had our air that we'd also feed through similarly. But the unique part here is that we also had what we consider our bypass fuel, where we actually would take some of our fuel supply, some of our hydrogen, and we'd feed through it and control it, and we would pre-mix it with our air upstream of the RDE. So I just have a few details in terms of the hardware here on the bottom left, if you wanted to know more about the system. And then also, I just kind of want to show here on the right, again, showing the rotating detonation engine with the zoomed in on the fuel injectors, but also a visual representation that, at least to me, was very easy to kind of understand some of maybe what we're going on here. It might be a bit of an oversimplification, but showing the flow, we're kind of looking at the domain radially in a sense here. So those green spots, and here I'm looking at the figure again on the far right, the green spots are our fuel lean areas, where that's where we have our air being injected towards us, but it's not nearby our fuel injectors. However, though, we have our locally well mixed region right nearby our discrete fuel injectors. By the addition of fuel premixing, essentially what we're intending to do is take some of those very fuel lean areas that are not nearby the fuel injectors, and by introducing a bit of fuel to that, we can, in a sense, kind of more normalize and make the domain here a bit more uniform in terms of its mixture ratio. So we achieve that by our bypass fueling, where hydrogen was injected. Again, we had our primary hydrogen that we inject into our rotating detonation engine that would feed in through our discrete fuel injectors, but we also had a secondary fueling line that would come through the bypass and would be injected into our air line as a jet and cross flow, with the length of the mixing chamber by the injection diameter ratio of 47, with also a diameter by our injection diameter of 8. So we had a pretty large, about a 30-centimeter long mixing chamber, where it allowed for our hydrogen and our air to mix before it is then injected in through our radial air slot that we had. So under this, we would assume that it was well mixed as it's entering our air plenum. But again, the motivations was that by premixing, we can achieve premixing achieved by fuel injection into the airline, we can make the domain a bit more uniform. So one of the things, though, that I would like to clarify is now the fact that we're introducing fuel into our air side. I wanted to bring up a few parameters that we use in order to define exactly, how much fuel we're putting into the rotating detonation engine and kind of where we're putting that fuel. So I would like to describe what at least we've coined as our baseline, or our base fuel air equivalence ratio, or Phi. That consists of our main air that we have feeding into the rotating detonation engine and our main fuel. So if we don't premix any fuel in here, our base Phi is just, it's the fuel air equivalence ratio that the rotating detonation, for all it knows, that's all that it's seeing here. However, with the introduction of a bypass fuel, where we're premixing, we then denote that as our global fuel air equivalence ratio, where that consists of everything, including any type of fuel that we've injected into our oxidizer, into our air. And thus, again, if we are injecting, we are premixing, then to the RDE itself, all that it knows is that this is the Phi that the detonations are seeing. And then also just to kind of describe between the fuel that we're feeding, as well as also the bypass. So the fuel that we're taking off of the main fuel line and premixing with our air, we consider that as beta, our bypass percentage, or our bypass ratio. So again, this is all going towards the idea of, can we confirm if detonation velocity distribution can be seen experimentally? And by what I've been mentioning in terms of premixing and injecting this fuel, again, the idea is we have now an experimental method where we can locally stratify our fuel and our air mixture. And before I get into some of the results, I also want to just mention how we're going to be looking at least for current studies that we have here, how we're going to be looking at how the detonation is changing based on the fuel stratification, the reactant stratification that it's propagating through. Just like with the numerics, where we look at detonation speeds, here we're also going to be looking at our detonation velocities. So how we achieve this and how it's pretty widely used in the community is that you look at your detonation waves through back-end imaging. You essentially put a high-speed camera at the exhaust that looks down the annulus of the RDE and looks at the detonation waves as they propagate about in a circle. We can, from that back-end imaging, we can extract the detonation wave speeds based on the frequencies in which these detonation waves are traversing about the annulus here. this code or the idea of taking back an imaging and extracting a frequency and thus a wave speed from it was first developed by the Air Force Research Laboratory, and a lot of the work behind that was done under a very big push under one of my co-authors, Dr. Taha Razag here at UCF, where he'd taken a lot of the work, expanded on it, and improved on it. But here I have shown for the specific experiments and the results I'll be talking about. Here we have our RDE here at UCF. We would fire it. We had a mirror here that was placed in between about 2 or 3 meters downstream of the RDE. That was just so that we wouldn't have to put our expensive high-speed camera directly in the exhaust path of the RDE. But we had our high-speed camera that we had imaging at 67.5 kilohertz with a 256 by 256 pixel resolution. And then here I just have a bit of an example showing the detonation surface, showing these detonation waves tracked over time with their annular position, in which we can essentially take an FFT of this plot here, and we can show our frequencies, the number of waves, as well as also the frequencies, and extract then the detonation velocities from that. And actually, Dr. Razag had used the code and validated it with some synthetic data that the Air Force Research Laboratory had provided, and here I have a picture there. So moving on into the experiment. So we decided to come up with 3 test campaigns, one of them where we kept the global fuel-air equivalence ratio constant, and I consider that as scheme 1. Here on the table on the right, what we did was we would take our baseline, or our base phi, our base fuel-air equivalence ratio, and we would modulate that from 0.95 to 0.83, where we would keep our global fuel-air equivalence ratio constant at 1, or at stoichiometry, and we would make up for that deficit in our baseline phi with a bypass percentage. So essentially what we would do is we would take, and I also have some equations here, just hopefully could make a little more sense. What we essentially do is we would take fuel from our main fuel line, and we would then bypass that in percentages of 5, 10, 15, and 20. We would bypass that and premix it with our air. So essentially, in terms of our main fuel and our main air, that fuel-air equivalence ratio drops because we are taking some of that fuel and siphoning off and putting it into our airline as premixing. So our global phi across the board, across these tests, is 1. So thus, to the RDE, globally, it is seeing a fuel-air equivalence ratio of 1. But one can, in a sense, say locally, as we increase our bypass percentage, we're increasing the amount of fuel we have in those fuel lean gaps. In our second scheme here, again on the table, we kept our baseline fuel-air equivalence ratio constant. So in this case, we kept our baseline phi at 0.9, but then we increased our global phi to 0.95, 1, and 1.05 by increasing our bypass percentage. And the reason for this scheme, as well as also for scheme 3 that I'll mention shortly, is that we want to see, we kind of have these different parameters between our main fuel, our bypass fuel, and our air. What can we change, and how can we change them to see what we get with our detonation wave speed velocity changes? So that's something that then we also look at scheme 3, where what we did was we kept our bypass percentage constant at 20%. So between, if you look at if we look at the bypass fuel that we're pushing, the fuel that we're premixing with our air, divided by our fuel that we're pushing through the main fuel line, for scheme 3, for those tests, that was kept constant at 20%, and everything else would adjust to that as we would sweep our global phi from 0.9 to 1.1 phi. So our baseline phi would react to that in order to meet these global phis. Throughout all of this, we had a constant flow rate of 0.7 kilograms per second. We chose that specifically because that was a pretty well-documented operating flow condition for this hardware, both for ourselves at UCF as well as also for those in the community. As well as also we had some baseline test campaigns that we ran to just look at non-premixed global phi of 1 as a baseline for scheme 1. As well as also then we had a baseline for schemes 2 and 3, where we essentially had no premixing and we swept our global equivalence ratio from 0.9 to 1.1. And again, here on the left side, I just have some equations to just kind of show the calculations there, but hopefully, at least based on my previous descriptions, it should be it should make sense. Now, again, going back to some of the graphics that I used earlier, and again, this was. I apologize if anything, if this makes it more confusing, but hopefully this can kind of understand or explain a bit of the motivations here. So we start here on the left side at A. This corresponds to our scheme 1, where essentially what we're doing, and I have here, this graphic here that I showed where it shows the radial injection of the air. We're looking at the RD injection from the side, in a sense. We have our fuel injection as these discrete micronozzles here, where then I have the orange here as like our well mixed, our around stoichiometric reactant mixture. Essentially what we're doing here, and I have these lines here as the global phi, is that we're taking our very localized fuel air equivalence ratio, or we have our very localized well mixed reactants, and by increasing our bypass percentage, we're taking these areas that are not nearby the injectors and we're raising up their fuel air equivalence ratio. So in a sense, we're kind of taking the domain here and we're making it more uniform in terms of fuel air equivalence ratio. So that is what scheme 1 is trying to accomplish here. Scheme 2, where we're keeping our baseline phi constant. Essentially what we're doing is we are premixing some of our fuel. So thus we have this bottom line that I have here, but by then increasing the global fuel air equivalence ratio, we're essentially taking our phi all across the board and increasing that up higher. And the point behind scheme 2 was we wanted to see if there was a difference in detonation velocity based on how we're stratifying and modulating the fuel and the fuel mixture here. Does that stand across the board of more than just a single global fuel air equivalence ratio point? Is this something where it spans across, let's say, a certain operation regime? So we centered around stoichiometric and we shifted from technically 0% bypass at 0.9 all the way up to 1.05, where we had a bypass percent of 22%. And then moving on into scheme 3, which I have here is C. Essentially what we're doing here is we're keeping our bypass percent constant. So the amount of fuel that we're pushing in, essentially, I guess just to be concise here, what we're doing is we're wanting to see if we increase the amount of fuel that we then push in through our main fuel, does that change anything? By keeping our bypass constant, but then increasing the amount of fuel we push into our main line, in a sense, we're almost further stratifying. We're in a sense further stratifying our equivalence ratio domain here. Does that change anything? Does the presence of just the premixed here to kind of replace those fuel lean zones, does that change just because we're now actually putting in a lot more fuel? So is it the fuel that's governing any kind of velocity, detonation velocity deficits, or is it the oxidizer, the air that we have here? To then just talk a little bit about some of the test here, I just wanted to cover some of the flow rates as well as also uncertainties that we had calculated here. So everything, I'll have them here, and everything in terms of results I'll have quoted. In terms of wave speeds, we had a pretty low uncertainty ratio, of about 1 meter per second. As well as also one of the things I'd like to introduce is that a parameter that I'm going to use quite often in the results is we take our detonation wave speed and we normalize it by the Chapman-Jugot detonation velocity, which is almost one can consider as like the idealized, 100% operating and efficient detonation wave. So we're essentially normalizing our detonation wave speed by the ideal. And if you're interested in terms of uncertainties and calculations, please speak with me afterwards. We have a pretty great and rigorous method for determining those uncertainties based on a really great paper from the past. So going on to the experiment, one of the things though that I just want to highlight, especially in the combustion community, as soon as you mention anything about premixed and it's nearby a flame, it's always a considerable safety issue in terms of making sure that you only have burning where you intend to have burning in your combustion chamber. So one of the things that we wanted to just make sure is that we were running these tests safely because of our premixing fuel and hydrogen and air upstream of an RDE. So we looked at the lean flammability limit for hydrogen and air, which is relatively known as about 4% at atmospheric conditions. However, in this other reference here, it was found that actually for turbulent reactants, that flammability limit, that lower flammability limit, might actually be pushed up to around 8%. So based on the amount of fuel that we are premixing, I have here a plot on the right showing that as you increase in your bypass percentage, and as you sweep from your global equivalence ratios from 0.9 to 1.1, so pretty much this is the region, this is the domain that we were testing in the experiments that I'm showing here, is that for our specific tests, we could only go to a maximum of 22% bypass percentage. And that was because at that point, we would start to hit that 8% pretty much cutoff, where at that point, the amount of fuel that we're pushing into our air supply and premixing can burn. So that's why, again, and you'll see that the table show again in terms of our experiments, that's why we had to cut off for scheme 2 in terms of our bypass percentage of 22%. If we went any higher than that, then there was a very big risk of flashback back through our airline. Okay, so starting to get into the results here. Here on the top left, I just have an image of some of our pressure traces that we measure of our fuel and our air. What I want to just showcase here specifically is, first off, I want to designate, when I talk about wave speeds here, I want to talk about it's during what we consider to be our steady state portion of our engine hot fire. So what we denote as steady state is that when we have no wave mode changes. By wave mode, we're considering wave number, wave speed, and frequency, and directionality as well. We have no wave mode changes for at least 90% of the total hot fire time. So here on this, and also, also that typically corresponds to very little changes, very minute changes in your flow conditions. So in terms of the amount of fuel and air that you're feeding into the RDE. So here I'm just showing where I'm showing the gold lines, kind of denoting the hot fire tests of 1 second. These black dots that I have, the black circles that I have here on the top, denote the detonation velocities we had calculated from back-end imaging. It's showing here that we eventually hit a point in which that is staying constant. It's staying horizontal over time. That's what we're denoting as our steady state. So anytime that I quote any detonation velocities, it's from this point, where essentially if we continue to feed the RDE with the propellants and the reactants it needs, it would essentially continue to stay along that velocity. As well as also showing a bit of the feed pressures as well to show that they're nominally constant. Another thing that I wanted to point out here is to make sure, especially when it's regarding injection, you want to make sure that your pressures are correct such that you're actually injecting, in our case, fuel into our air supply here. So one of the things I want to show here on the red lines, the solid red line was the upstream of our choke orifice, which we use to regulate our mass flow rate in a sense. Our upstream and our downstream was about a ratio of 2 pressure drop, which means that our choke orifice, we're using it correctly. We have a high pressure drop, which means we are then compressible, and it's a sonic choke orifice. So it just means that the pressures that we have and the amount of fuel that we're actually pushing through our bypass line is not unchoking, and thus we have a handle of the mass flow rate there. Another thing I also want to show here is that the downstream of our bypass fuel was considerably higher than the downstream of our air. So it just means that the fuel injection was at a higher pressure than the pressure of our air as it's entering the RDE, or as it's entering the mixing chamber, which then enters the RDE. So it means that we're constantly injecting during the test run. So it's mainly just to show that we've done our due diligence in terms of understanding that when we're injecting hydrogen, we are in fact injecting the hydrogen that we are intending to do. And I have a video here of a test fire. I'm going to refrain from playing it because I'm not quite sure if the volume is up on this. I don't want to blast anyone's ears. But I do have a picture here on the bottom right, zoomed in a little bit, of what the exhaust of the RDE looks like as it's detonating. So then moving into the results for scheme 1, where again, what we're doing is we're taking our global fuel air equivalence ratio, we're keeping that constant. Here on the left, I have, and we kept that constant as we are increasing our bypass percentage from nothing, so no premixing at 0% bypass, all the way up to 20% bypass percentage. Here on the left, I have some figures of detonation velocity over our bypass as we're increasing our bypass percentage. I also, as I mentioned before, have this metric here where we're normalizing our detonation velocity by the CJ detonation velocity here. So some of the things I'd like to point out as well is that our black line that we have here on these left two plots is our baseline case. As I mentioned, we took a baseline for scheme 1 where we had no premixing at all. We had no bypass. So what's immediately seen is that as we would take some of our fuel from our main fuel and we would mix it with our air line, so thus increasing our bypass percentage, we would see across the average of tests that we took that we would have an increase in our detonation velocity and increase according to our normalized UCJ. Now, one of the things I would like to point out, and this was something that we considered as we were looking at our results, when I quote our CJ detonation velocity, that is dependent on the fuel air equivalence ratio that you're looking at. So here I want to show on the right, since we have essentially two equivalence ratios that we have defined, one of them being our baseline phi, the other one being our global phi, I just want to show the difference between whether some of the figures here I'm quoting based on whether we're normalizing it by our global CJ or our baseline CJ. So I show here, if we use our baseline CJ, we see a much higher increase in velocity as we bypass. But we don't think that that's really a good representation of what we're seeing here, because to the RDE, to the combustor, what it's seeing is the global fuel air equivalence ratio. For all it knows, it doesn't really matter whether anything's been bypassed. All it sees is that as it's propagating about the annulus, it's hitting on average this global fuel air equivalence ratio. So we normalize it again by global CJ, and we think that that's a bit more of a realistic understanding of what's going on here. So again, I just want to note the general increase in detonation wave speeds with increasing bypass percentage. We had a peak at 15% bypass ratio, but we think that that peak there can be accounted for a wide spread of our wave speeds that we had recorded. So across these tests for scheme 1, we had a variability of our global phi by about plus or minus 0.01, and that corresponds to about a 4 meter per second change in your detonation CJ velocity. So these error bars here are primarily coming from global phi variations, as well as also nominal variations in wave speed that we would see across tests, even of identical flow conditions. And again, I just want to mention all wave speeds here are quoted during stable wave modes, and we check for transients across the board. Then we start to get into some of the fascinating, because again, the previous example that we've seen is that there was an increase in detonation wave speed, albeit it might be small, but we see that there is some kind of effect on wave speed based on bypass percentage. What we see here is we want to further investigate that, and that's where scheme 2 comes into play, where again, we kept our baseline phi constant, where we had a baseline where we swept our global fuel air equivalence ratio from 0.9 to 1.1. And then again, we kept that baseline phi constant, and we would increase our global phi by increasing the amount of fuel that we would premix into our engine. And again, the purpose of this testing scheme is to see if we would see an increase in detonation wave velocity across more than just one global fuel air equivalence ratio. I guess one thing I should highlight, in the previous scheme, everything was taken with a global fuel air equivalence ratio of 1, whereas in this case, we're spreading from 0.9 to 1.1. So what we found is that as we would increase our global fuel air equivalence ratio, and thus increasing our bypass percentage, which I have noted here, as we would increase from 0.9 to 1.1, where 0.9 global phi, we had no bypass, we had no premixing. We would increase to 6%, 14%, and then 22%. As I mentioned in the past, we were capped at 22% based on our flow rates and based on our engine, because after 22%, we would start to hit the lean flammability limit, and thus it would be unsafe for us to premix at that point. It shows here that we have these trends between our baseline detonation velocity and our premix detonation velocity. They start to spread out, and that's very inherent in the detonation velocity standardized by UCJ, where it's showing that we're having an increase in our detonation velocity. Here, what we're seeing in our baseline is as you increase in your global phi from 0.9 to 1.1, you're actually decreasing in your normalized detonation velocity. Whereas in the premixed case, we're almost in a sense steadying out. And so some of the implications here is that maybe the premixing can extend your highest detonation velocity operation in your RDE, potentially. However, though, what's very interesting is then in showing the results from scheme 3, where we kept our bypass percentage constant. And again, the baseline tests that we ran were the same for scheme 2, but in this case, what we did was we kept our bypass percentage constant at 20%, and we would span our global fuel equivalence ratio from 0.9 to 1.1, where our local or our baseline phi would then change in order to respond to that. What's very interesting here is that we see a very similar trend between our baseline cases and this scheme 3, where we kept the bypass percentage constant at 20%. Again, the baseline was the same for scheme 2. And also one of the things I'd like to point out, the reason why we picked a bypass percentage of 20 was just, again, based on our lean flammability limit of 22%, we thought 20% would be a very drastic difference in terms of the amount of fuel we're pushing through our main line. As well as also that was about where we saw the widest gap between our premixed versus our non-premixed velocities. But what's interesting is when we put these two plots, when we superimpose them on each other, we see pretty much the same phenomenon. So one of the things that I'd like to specify is that in these phenomenons, we're seeing two relatively different, in a sense, stratifications here, or different domains that we have here. In scheme 2, which I have shown here as the red dots, here we're increasing our bypass percentage. We go left to right from 6% all the way up to 22%. Whereas in the blue dots we have here, we're keeping our bypass percentage constant at 20%. And in this case, we're seeing pretty much the exact same trend. Now, of course, with a bit more resolution, a bit more test, we could maybe try and get specifically what that trend is. But at least qualitatively, what we're seeing is that these trends are almost identical in both the detonation velocities as well as also normalized by UCJ. So what we can conclude here is that an increase in the wave speeds is independent of the bypass percentage. It is more dependent on the fact that you have the presence of premixed fuel in your air. And again, I just want to call out that the difference in for example, with a 6% bypass ratio that we have here, we saw that there was already a bit of an increase in our wave speed across the board. So if we look at 0.95 global fuel equivalence ratio, we have an increase of, 0.5%, velocity normalized by UCJ, and that corresponds to a mole ratio of hydrogen to air of only 2%. So that's even below. That's even half of the lean flammability limit, not even considering turbulence. So even just the presence of that small amount of fuel that is not considered to be ignitable, we have an increase in our detonation velocity. Also, before I get into the conclusions, one of the things we also wanted to point out here, in the community, it's often been theorized that wave mode is a result. So wave mode being the wave speeds as well as also the number of waves and their directionality is a result of your local stratification. And we're kind of hinting at this in this work here, where we would have detonation velocity changes based on our fuel and our air stratification. But also what we saw was that our actual wave number changed as we would have our baseline, our premixed. It wasn't very often. But specifically for this RDE architecture, for the flow rates we run, a 3-wave mode, so 3 waves propagating about in a circle, is very uncommon. And for our baseline cases, non-premixed, for both this campaign as well as also everything else we run with this architecture, we would have pretty much no cases for around these flow conditions where we would have any type of 3-wave modes. Here in the premixed case, we had 3 out of our 55 tests at which corresponds to about 5%. Where we would have these 3 wave modes. Typically, your wave mode in terms of wave number is affected by your injection geometry, as well as also your flow rate, your mass flux. Here, just based on our fuel stratification, we would have the presence of these 3 wave modes. Now, again, this would take a lot more investigations in the future. Also, one of the things I'd like to point out, these 3 wave mode cases that we had here, where I've highlighted the bypass percentages these occurred at, we did not include these in any of the results we showed in the previous schemes here, again, because they were very much outliers. But it was very interesting, the fact that those outliers really even revealed themselves. So in conclusion, we investigated 3 different configurations, or what we're considering injection schemes, to determine the effects of our premixing on the rotating detonation wave performance. We had our constant global fuel equivalence ratio scheme. We then took our constant base fee and our constant bypass percentage. Essentially, what we conclude is that just the presence of premixing itself increases your detonation wave speeds. It doesn't have to be a lot of premixed fuel in your air. It just has to be a little bit, just the presence of it. And we found that, again, this increase was independent of the amount of, this increase in our detonation velocity was independent of the amount of fuel premixing, and appearing across a range of fuel equivalence ratio conditions from 0.9 to 1.1. So thus, variations on the detonation velocity due to fuel stratification can be seen experimentally based on your localized stratification. And based on these results, rotating detonation, combustors, and engines with a stratified injection scheme can be improved by a low level of premixing. So before I close out, I just wanted to cover just a few more things. What I really admire about this forum here is that we have a lot of researchers present, and I want to talk a little about some of the future work we have here. One of the things we actually want to do is we'd like to seek some CFD collaborations with anyone here who's willing to and has the capabilities for it. So our current capabilities in terms of injection and looking at mixing and stratification are largely in cold flow injection. We've worked with some other injector types we have here at our research laboratory. But what we could be looking for is anyone with 2D or even possibly 3D capabilities of reacting, of detonation propagation. Thus, we could then investigate the differences between non-premixed and partially premixed for this injector configuration. So again, we've based a lot of our previous work on just general simulations of detonation propagation through stratification, but how does that compare to what we're doing here, where it's in an RDE? So if we could have some CFD to kind of pair with some of this work, then we think that it could very strongly encourage some of the conclusions that we have here. Well as also on our end, we also have some additional experimental chemiluminescence imaging, where we have optical access for this RDE now. So we can run our filtered chemiluminescence or any kind of laser fluorescence, and we can try and look at detonation wave structure and see if the structure itself is changing based on our premixing. And then I think that the final thing in terms of some stuff here, I actually will gloss over this because I think it's probably not necessarily my place to talk about some of this, but just know that in terms of the general RDE community in the future, there could be a lot more solicitations for general RDE 3D simulation work. So please be on the lookout for any papers that might be coming up about boundary conditions for experimental work that could be used to fuel some simulations that you all might be running. So again, I'd like to acknowledge some of the sponsors here, as well as also our co-authors. And I'm sorry for leaving us only for 6 minutes of questions, but thank you for your time. And if you have any questions, I'm now open for questions.
Thank you for presenting. So I guess as a quick first question, and then if anyone else has additional questions, you can put them in the chat or just unmute yourself, raise your hand. But you said like adding fuel either way helps. Do you think there's one that you would personally find better for any particular reason, or it really doesn't matter? Like, is there one that you would prefer, or like you think would be more useful than the other, or easier to implement, or better for like TRL in any way?
Yeah, absolutely. So, all of us here, knowing combustion, ideally, if you could have perfectly premixed reactants, that results in your best combustion ever. But at least, practically, it's very difficult to do that in a safe fashion to have perfectly premixed. And also then you have to define what you exactly mean by perfectly premixed. So at a certain point, again, for safety concerns, you don't want to be injecting something that's too premixed in your combustor, again, for the risk of flashback of flames entering into places that you do not want them to enter in terms of your combustor. So I would say that in terms of injection, we want to stay well below that lean flammability limit. So for example, with what I showed, that just with a 6% bypass ratio, you had an increase in your detonation wave velocity by 10 to 20 meters per second, which again might seem pretty insignificant, but it just shows the fact that with a very lean amount of fuel premixing, again under very safe procedures, you have some kind of change in your detonation wave velocity. So I think that that's more likely to be implemented. So a very lean injection of your fuel or of your fuel into your air, on the order of maybe like 5 or 6% is enough to have a change. I think that's more practical and thus more easily implemented in terms of usage for the RDE as a technology. And then I think one of the things that I also want to just cover, and this kind of feeds based on your question here, is that we would very much like to investigate this further in terms of a wider operating regime here. So we only looked at just a global fuel equivalence ratio from 0.9 to 1.1, but perhaps this could be utilized in terms of extending our operability limits in general for the RDE. What if we push into the very lean regimes of the RDE and maybe like 0.5 or 0.6 where we stop to see detonations? Maybe by the usage of some of this premixing, we can actually extend the limits of detonation operability in these engines. That could also even mean the same thing on the fuel-rich end. So that's something that we would very much like to investigate. Of course, that's going to be heavily dependent on our capabilities, again, to make sure we're doing this in a very safe fashion. But that's also a potential other application for this.
Thank you. Yeah, that'd be neat to see. I think Shem has a question, so if you want to unmute yourself, you can.
Thanks, Robert, for the presentation. I was wondering if you considered the other injector and putting that at the upper flammability limit, so you'd have one at the lower and one at the upper, and if you think that would make much of a difference or not.
Yeah. That's something that we would definitely want to look into. So at least in terms of looking at the flammability limit, our primary utilization for that was just to make sure that we weren't injecting too much fuel. We saw a few other research papers and previous investigations that looked into premixing, especially with RDEs, and they weren't too, let's just say that they were very open about some of the system failures they had because of flashback. So we primarily used the lean flammability limit just to make sure that we wouldn't run into any issues with damaging our hardware or our feed lines. But as I mentioned to Rachel's question, we very much would like to investigate all the different limits, whether it's the limits of the RDE itself and its operation, as well as also, as you had mentioned, we could look at the flammability limits on both the lean side and also the upper side as well.
Thank you very much.
And then I think Charlie has a question if you want to go ahead and ask it.
Yeah, have you guys looked at premixing somewhere farther downstream so you don't have tubes of premixed gas flowing into the combustor, but premixing right into a manifold or an injector?
Yeah, absolutely. So I think one of the reasons why, at least for this investigation, we specifically chose somewhere pretty far upstream was just to make sure that it was pretty well mixed. Of course, it would actually be important for us to try and fully characterize how premixed it actually was. I mentioned 30 centimeters in length in a pretty wide diameter tube, but also, just because we're injecting fuel into it doesn't necessarily mean it's actually premixed. There could be local pockets of hydrogen. So we had that volume as pretty extended to try and ensure as much as possible that it was premixed our hydrogen in our air. What we would see is if we decide to push that further downstream, so closer to our actual air injection point, is that unless we were very considerate about how we're injecting our fuel in there, it might not be as premixed as we're imagining. We might have some areas of our air radial slot that might have more hydrogen premixed into it as opposed to others. So potentially with the idea of maybe some kind of like circular ring, or in a sense, almost another injector set of hydrogen premixing into our air, by all means, that is pretty important because, number one, it also just means that, yes, we have less physical volume of premixed gas upstream. So we can, limit any type of failures that we have, or at least we could try and localize it a bit better, as you're hinting at. But also in general, it takes your entire system and it really takes the footprint of it and really minimizes it. So that's a very great idea. We would love to go into that more. And I think in terms of integration, that's something that we definitely can do. So yeah, we'll probably be investing in that in the future, again, given our current results. So yeah, thank you for mentioning that. That is a good idea. It was definitely in our minds, but now it's at the top of my mind again. So it's encouraging.
Awesome.
Okay, and then does anyone have any other questions? One last call for them.
Or maybe let me ask.
So I guess with that, we'll thank our speaker again. So thank you, Rob. It was a great talk and it was really fun to listen to. Next week, our presentation, or I'll be speaking for the presentation, and I'll be talking about flame generated turbulence for flame acceleration, detonation transition, and detonation propagation. And that'll be Friday at 10 a.m. And then I'll send an email about that out later this week. But yeah, thank you everyone for attending and have a great Friday. And then yeah, Rob put his email in there if anyone has any other questions. But thank you.
Thank you, Rob.